the commercial cells. That means, in our day to day life, we use different types of cells. Some particular types of cells are batteries. Battery is nothing but when different large number of cells connected in series, then we call it as a battery. In our daily life, we use different types of cells or batteries, starting from the motorbike which we run, or the motor car that which we run is works on battery. The inverters we use also works on battery. The cell phone we use works on the battery. Torch light, transistor, radio, all this work on battery. But in each case, we use different types of batteries, where the design is different, the size is different, the material used is different, and of course, the reaction involved is different. But anyhow, all these are one or the other type of galvanic cell, electrochemical cell. The principle involved is the galvanic cell principle, reaction is the cell reaction, redox reaction, but depending on the purpose and requirement, different types of cells have been designed. Then let us see, in these cells, some of them are chargeable, some of them are non-rechargeable. Some of the cells are rechargeable and some of the cells are non-rechargeable. For example, the Leclanche cell, what we use in transistors and torch lights, is a non-rechargeable. This Leclanche cell is nothing but commercially we get it in the brand names like Eveready battery, Nippo battery, right. These batteries, as all of you must have seen, this is what is called a Leclanche cell, and these batteries are non-rechargeable batteries. If once the battery stops working, we cannot recharge it, we cannot reuse it, it has to be thrown out, again we cannot use it. But whereas the cell battery that we use in our cell phone is a rechargeable battery, that is of course lithium ion battery, that after use again we recharge it and we use it. That is the reason of course our cell phones regularly we put it for recharging and we will be keep using, and as you know very well that the battery can run up to 1 year or 2 years depending on the usage. This is rechargeable. In the rechargeable battery, what happens is, if once the cell reaction is moving in one particular direction and the electrodes gets discharged, then on recharging again the cell reaction can be reversed. But in non-rechargeable batteries like Leclanche cell, if once the cell reaction is completed, the reactants we cannot get it back, and same is the principle in the car batteries also. If once if the battery gets discharged, then we add some distilled water to the battery and we recharge it, so that the cell reaction will be reversed, and the reactants initially what we take again we can get it back and further can be used. So let us see one by one, and in addition to all this also we have something special class of cells called fuel cells. In the fuel cells, the principle is the gases, the hydrogen and oxygen gases, not necessarily hydrogen and oxygen, even it can be a hydrocarbon, hydrogen or any hydrocarbon gas is burnt in presence of oxygen, and the energy liberated is used as a source of energy, and that is fuel cells. So all this one by one, now we look into it. So commercial cells are the cells we use it for commercial purpose. So these are classified as primary cells and secondary cells. Primary cells are non-rechargeable. these are rechargeable. That means, if once the cell reaction is over and if once the cell completely gets discharged, this cannot be recharged. This can be recharged and they can be rechargeable and can be reused. Here the best example is a dry cell, which otherwise we call Leclanche cell, and mercury cathode cell. And here we have the lead acid battery, which we use it in car and bikes and inverters. Second one is NiCad, that is nickel cadmium battery. Then of course we have lithium and lithium ion batteries, which we use it in cell phones. So this is the classification. And besides this, among the commercials also what we have is fuel cells. In the fuel cells, it is the gaseous fuels like hydrogen or hydrocarbons and oxygen gas are used as fuels, and the energy liberated in the combustion of these gases is used in generating the electric current. So these are the, this is one type, this is second type, and this is third type. Now let us see each type with examples one by one. The dry cell is the one which we use it in our transistors, radios, torch lights. This commercially we know them as Eveready battery, Nippo battery, like that. In that, as you see, first we have a grey colored cylindrical shaped vessel. That grey colored cylindrical shaped vessel, of course, on top of which a red wrapper by Eveready, blue wrapper by Nippo, those labels will be there, but actually it is a grey colored box or vessel. That is actually a zinc container. That is anode. Anode is zinc container, and at the middle, as you can see, there is a steel tip that goes till the bottom of that vessel throughout, and that is what you call a cathode, which is a graphite rod. So cathode is a graphite rod, and the space between this anode and cathode is filled with manganese dioxide, is filled between the electrodes, So it is rather the cathode is surrounded by manganese dioxide powder, like this also graphite rod. I can write surrounded by manganese dioxide powder, like that also we can take it. So it is a container, in between there is a graphite rod, and this is in between there is a manganese dioxide powder. Then electrolyte is moist paste of ammonium chloride and zinc chloride, and the cell reactions is that at anode it is a zinc gets oxidized to Zn2 plus, and at cathode it is manganese dioxide. At cathode here you have manganese dioxide with ammonium ion from ammonium chloride to MnOOH plus ammonia, right. This is the reaction, this is the reaction at anode, and this is the reaction at cathode. These are the two cell reactions. Now here this is a non rechargeable. Why is it non rechargeable? Because Here the zinc ion and ammonia that is formed respectively at anode and cathode, they both again will react. Zn2 plus will react with the ammonia and which acts as a ligand and will form a tetramine zinc complex, which is highly stable. Now this complex being highly stable, this cannot be dissociated back, so you cannot get back zinc ion. As we cannot get the zinc ion, the anodic reaction cannot be reversed, and similarly the ammonia produced at the cathode also cannot be converted back into ammonium ion, as the both are involved in the formation of a highly stable complex. So, the cell reaction cannot be reversed. So, if once the cell reaction is completed and if once the cell gets discharged completely, that again cannot be used, that battery should be thrown out. And here the cell potential, as all of you must have seen on those batteries, it will be written that E is equal to 1.5 volts. Each battery is of 1.5 volts. Suppose if we want for a particular transistor or it requires 6 volts, then we use 4 such batteries in sequence. In torchlight, which works at 1.5 volts, we use either 1 or 3 volts torchlight requires what you call 2 batteries. So, depending on the net voltage that is required, we increase the number of batteries, and this is the cell potential, and this is the, so anode is zinc container, cathode is graphite rod surrounded by manganese dioxide paste, electrolyte is moist paste of ammonium chloride and zinc chloride, and at anode, that is the container itself, zinc gets converted to Zn2 plus, at cathode manganese dioxide paste, manganese dioxide powder, that what we use converts to MnOH with ammonia, and the ammonia formed at the cathode, zinc ions at the anode, both will combine to give a stable tetramine zinc complex. This is the overall sequence of reactions and the working of the dry cell or Leclanche cell, and the cell potential is 1.5 volts. This is a simple method. So, this is all of you must have seen the used batteries. If you try to break up and see a black powder that comes out, and a rod also you can see, that rod is graphite rod, the box appear, that vessel appears grey in color, that is zinc container, and black powder that you see, that black powder is manganese dioxide powder. So, this is the cell reactions. Now, let us see the other type of cell, that is zinc mercury, zinc amalgam battery. Let us see the amalgam battery. The next is amalgam battery. In the amalgam battery, the anode is zinc amalgam. Amalgam means a addition compound of mercury and other metal. The other metal here is zinc. So, an addition compound of zinc and mercury, which is an alloy, a zinc mercury alloy, is amalgam. Then cathode here is mercuric oxide plus carbon, and electrolyte is a paste of KOH and zinc oxide, moist paste of zinc oxide and potassium hydroxide, that acts as an electrolyte. The cell reactions is of course like in the dry cell, the anodic reaction here also it is zinc amalgam to Zn2 plus metallic mercury or the liquid mercury, and this is of course in presence of the OH also you will get H2O, and at cathode it is a HgO plus H2O reduces to mercury liquid and of course 2OH minus. Overall the cell reaction is that zinc amalgam with mercuric oxide solid the zinc amalgam and solid mercuric oxide. Zinc amalgam is anode, solid mercuric oxide cathode in presence of OH, that is this, which acts as an electrolyte, that will give you what you call zinc oxide and mercuric liquid. This is the overall reaction, and here the cell potential is 1.35 volt. Here the EMF of the cell is little less. So, is the reason that this amalgam cell is useful mainly in low current devices. What are the low current devices? Hearing aids. Hearing aids, what is used, we use for the hearing purpose, for deaf people that is used, and also flash cameras. In the flash cameras, as of course now digital cameras, we are using the rechargeable battery, but in the earlier days where we had this normal flash cameras, there we used to have these batteries, and that is in those cameras this is used because those cameras will work at a low voltage, that is 1.35 is sufficient. So, in such cases this what you call amalgam batteries are used, and this is also if once the cell reaction is completed, as the mercury liquid, zinc oxide is a highly stable oxide. Zinc oxide is a highly stable oxide. If once it is formed, it is not possible for it to dissociate back into zinc, and it is not possible to form the amalgam back. So, is the reason that if once this is done, if once the cell gets discharged completely, it is not possible to recharge it and cannot be reused it. So, is the reason that this is also non rechargeable battery. Now, we go to the chargeable batteries, that is secondary batteries. Secondary battery. The secondary batteries are the batteries which we use again for regular commercial applications and which are rechargeable. These are rechargeable batteries. The best and well known example is the batteries what we use are the lead acid battery. Which we use it for in car battery, bikes, inverters, so on and so forth. In this, the anode is grid of metal plates, grid of lead plates, cathode is solid lead dioxide, and electrolyte is 38% sulfuric acid, aqueous sulfuric acid solution, 38% aqueous sulfuric acid solution. Here what happens is that at anode it is lead reacts with sulfuric acid to give PbSO4 plus 2H plus 2 electrons. This is at anode. At cathode it is PbO2 plus H2SO4 plus 2 electrons, or this H2SO4 you write it as 2H plus SO4 2 minus, that will give you PbSO4 plus what you call 2 OH minus. Overall the cell reaction is that Pb plus PbO2 plus 2H2SO4 to give 2 PbSO4 plus 2H2O. So, here one common factor, common product what you observe both at anode and cathode is that at anode lead from 0 oxidation state getting oxidized to +2, where the product you are getting is lead sulphate, and at anode lead at +4 oxidation state getting reduced to the again the same product lead sulphate. 0 is oxidized to +2 where you are getting PbSO4, +4 is getting reduced to PbSO4. So, at anode and cathode you are getting the same product, and both cases of course it is the 2 electrons that is involved. So, the N factor for both the reactions, for anodic reaction the N factor is 2, for cathode also the N factor is 2. Overall it is the N factor is 2 for the overall reaction. So, here another very important thing that one has to note down is that the normality of sulfuric acid here used is equal to its molarity, because 2 moles of sulfuric acid required 2 moles of electrons, that is N factor is 2. So, as N factor is 2 for 2 moles, therefore, for 1 mole of sulfuric acid N is equal to 1. So, the N factor is 1 for sulfuric acid in this case. As the N factor is 1 for the sulfuric acid in this case, the normality of the acid is equal to molarity of the acid. And so, here the things what one has to observe is the anodic product, cathodic product both are same, sulfuric acid molarity and normality are same. So, like this, and both oxidation and reduction in both the reactions the product is the same. And another very important thing is, if once the lead sulphate is formed, for this if you add distilled water, if once the cell reaction is completed at both anode and cathode you will get lead sulphate. If once you add distilled water, this lead sulphate will dissociate into Pb2 plus and SO4 minus ions, and the Pb2 plus oxidizes to PbO2, Pb2 plus reduces to Pb, and the cell reaction is reversed. That is the reason that very frequently after quite a long use, I think you people must have seen that in car battery we add distilled water, we go to petrol pumps and we add distilled water many times, or when we give it for servicing, the service fellow will add distilled water into the battery. What is the reason for the distilled water is added to the battery? The reason is that when distilled water is added to the battery, then the lead sulphate will undergo hydrolysis. Lead sulphate will undergo hydrolysis, get back yours due to hydrolysis, you will get back sulfuric acid, you will get back Pb2 plus as oxidized into Pb plus 4 reduces to Pb, and you will get back the original anode and cathode reactants, and the cell reaction again can be proceeded further. So, here recharge can be done. This is what is the principle in the car batteries. Now, we will see the other type of rechargeable battery, that is what we call NICAD battery. NICAD battery, as the name suggests, NICAD, that means it involves nickel and cadmium. The anode here is cadmium metal, solid cadmium metal, and cathode is nickel hydroxide, solid nickel hydroxide. And of course, this nickel hydroxide, like in the lead acid battery, as we have a grid of lead plates, like that here of course, it is a metal grid that it consists of. And the electrolyte here is any base that we can use. Electrolyte is sodium hydroxide or potassium hydroxide, and the cell reactions is that cadmium, this is of course the anodic reaction, 2OH minus to cadmium hydroxide, and at the cathode the nickel hydroxide NiOH you can write, or NaOH twice that you can write, with water it changes to NaOH twice. So, this is the product at the cathode, or if you want to write reactant only, that you can write it as NiOH, where nickel is in +3, product is this. So, either way we can write. So, this is how it is, and finally, the reaction is that cadmium with nickel basic oxide of nickel to give, this is cadmium hydroxide and nickel hydroxide. And once again here the cadmium hydroxide and nickel hydroxide as what we get, like in the case of lead acid battery, as once we add distilled water, as there the lead sulphate undergoes hydrolysis and produce the H2SO4. Similarly here, as these are of course the cadmium hydroxide, nickel hydroxides are being the bases. So, as once we add distilled water, if once cadmium hydroxide and nickel hydroxide deposits respectively at anode and cathode, as a reaction once completed, then if you add distilled water, again the required number of hydroxide ions in the solutions as we can get, and the cell reactions can be reversed. So, this is again on adding water, dissociation takes place and cell reaction can be reversed. And here E cell is equal to 1.3 volts. So, this Nicard batteries are again this is nothing but what we use in the Duracell. The Duracell batteries is what we can see is this Nicard batteries, which of course again nowadays we are using it for the torchlights and all. But of course, this Nicard batteries are not the ones that what we are using in cell phones. In the cell phones, the batteries, the cells that what we use is lithium ion batteries. They are entirely different, and there we have a lot many types of versions over there. In some cases it is the lithium ion, in some cases it is the lithium metal. So, there is a different cases over there, right. So, this is overall chargeable and rechargeable batteries. The next what we have is commercial cells. In the commercial cells, next in the commercial cells what we have is fuel cells. In the fuel cells, as I told, that it is the gases that we use, and once we see that fuel cells also. In the fuel cells, gases, combustible gases like hydrogen or hydrocarbons are burnt in oxygen. Here, as for when it comes to cell construction, here we have two carbon rods are used as electrodes, and there of course porous carbon rods, and in this sodium hydroxide is used as a electrolyte, hydrogen and oxygen gases are passed inside through porous electrodes, and the cell reactions are that at anode oxygen to 2H2O, at cathode it is 4H plus plus O2 plus 4 electrons to 2H2O. Overall the cell reaction is that this 4H plus, which is nothing but 2H2, 2H2 plus O2 gives 2H2O. This is the overall cell reaction. So, hydrogen and oxygen gas, hydrogen gas is burnt with oxygen, whereby water is produced. This is the overall cell reaction. So, here in a use electrolytic chamber, carbon rods, porous carbon rods are placed, sodium hydroxide solution is added into the tank, which acts as an electrolyte. Hydrogen and oxygen gases are passed through porous electrodes. Hydrogen gas is allowed to burn with oxygen, water is being produced, and this reaction is highly exothermic reaction. The reaction here highly exothermic. So, the energy used here, that is converted into electrical energy, right. So, and this is the overall reaction, and the many use and very basic purpose of this fuel cells is that, first of all, theoretically they are supposed to be 100% efficient. So, there is supposed to be no wastage of fuel, but in reality 100% could not achieve so far, but it is highly efficient. The efficiency of the cell we determine by efficiency. Efficiency is determined by delta G by delta H. Delta G is the free energy change of the reaction. Delta G is nothing but, as already we told, it is minus NFE. This delta G by delta H minus NFE by delta H, this is work. The work extracted, efficiency of not only fuel cell, efficiency of any galvanic cell for that matter, efficiency of the any galvanic cell can be determined as the net work extracted, that is delta G or minus NFE, to the net energy change involved. So, work extracted per unit energy change, that will give you the fraction of work that is obtained. So, that is what is actually the efficiency. So, the main advantages of the fuel cells is that they are supposed to be 100% efficient, but of course, practically 100% efficient still not yet achieved. Second thing, as the gases used are hydrogen and oxygen gases or any other hydrocarbon gas, which are normally expected to be non-poisonous or non-polluting. Hydrogen is a non-polluting. So, in any conventional batteries while we are using, there is a lot of environmental pollution related problems, but in this case of fuel cells, no such problem arises. Second thing, as we told, it is supposed to be highly efficient, and third, that here water is produced as a byproduct which can be used for any purpose, especially the fuel cells are first used in Apollo space missions, right. So, here the water produced is being given for drinking by astronauts. So, this is another added advantage. Keeping all this in view, environmental related problems, high efficiency and useful byproducts, that is water. Keeping these three in view, fuel cells are found to have many applications, and in coming days the future is more with usage of fuel cells rather than any of the other conventional commercial cells. So, this is another very important research area in the field of electrochemistry.